Cool. So my name is Arvind. I think Nihal spoke a little bit about me. But yeah, I come from a data engineering background. I've worked for a lot in data engineering. I spent a bunch of years at Meta and also doing consulting for a bunch of different brands. Currently, I'm working on my startup called Crux AI. Here's my QR code if you want to get connected on LinkedIn. But we're going to talk about RAG. I think you've heard this term already a lot of times today. But quick show of hands, how many of you know what RAG is? Right, pretty much everyone, right? And how many of you have tried building a prototype RAG, a toy prototype RAG? Okay, several of you. How many of you have shipped your RAG to production, like a customer-facing chatbot? Okay, just a handful of hands there. Cool, cool, awesome. So for the uninitiated, a RAG is a very interesting technique. It's a technique that allows you to connect external knowledge base or external data to enhance the power of LLMs, right? Imagine if you want to launch a chatbot on your website and you want the chatbot to answer questions about your products and your services. An LLM is not going to be able to do that by itself, right? Because it doesn't have the data. It's not trained on the data about your products and services. That's where RAG comes into play. It's called retrieval augmented generation. You basically connect an external data source, and when a user query comes in, you dynamically retrieve the right context to answer questions that the user may have, right? There's a quick diagram here. The bottom section is where you see the knowledge base. You got to chunk your data, you got to embed it, and you got to store it in the vector database. And then when a user query comes in, like I said, you embed that query itself, and then you do some sort of semantic matching, semantic search on your data, and then you fetch the right context so that you can then send all of that to the LLM and answer questions that the user has asked, right? Now, that's the bare bones version of RAG. It's called naive RAG, right? It's the very basic version of RAG. It's the best starting point if you're just getting started, right? So that's the minimal number of components, right? There's just retrieval, there's just the prompt engineering bit, and there's nothing fancy there, right? Now the problem is that that doesn't get you very far, right? In the sense that will still suffer from hallucinations, that will still suffer from reliability issues, right? So there are a bunch of failure points that happen, right? In hindsight, I should have probably increased the font size in my slides. Is it visible for you folks out there in the back? Yeah, cool, awesome. So yeah, like I was saying, there's a bunch of failure points. So for example, the query that the user is asking, it may be ambiguous, it may be an unclear query, it may be a complex query. So you're not able to fetch the relevant context based on that query in its raw form, right? On the data ingestion side, your chunking may be ineffective or inefficient, right? Suboptimal. Consequently, you're not able to fetch the right chunks of data when you do retrieval, right? Similarly, your embedding model that you're using may not be sufficient to establish the semantic relationship, to represent the semantic relationships in the data, right? Your index may be suboptimal. Your retrieval may suffer from low recall, low precision, and so on and so forth, right? So overall, a RAG has a lot of different moving parts, and each part can suffer from a failure point, right? What happens when you have a lot of moving parts? You have a lot of failure points, right? So that's the biggest problem with RAG, right? So what we're going to do today is we're going to take a look at how do you build an optimized RAG system that you can ship to production, right? So that's a very broad topic. This slide kind of gives an overview of all the different techniques, and even this is not exhaustive by any means. But if you see, there are just so many different optimization techniques when it comes to RAG, right? So I'll give a quick overview of this in probably about 1 or 2 minutes. And then what we'll do is we'll look at a a few selected optimization techniques, because obviously we won't have time to go through all of them. But happy to share pointers after this talk if you're interested in a specific technique that you want to learn more about, right? So very quickly, the optimization techniques fall into 4 broad buckets, right? So that's pre-retrieval optimization, which is basically improving the quality and retrievability of the data, right? So that's where you do things like improving the information density of your data, optimize your chunking, improving the embedding model or trying out a different embedding model, and a bunch of other things, right? We'll look at a subset of those. Within the retrieval side, that's where you improve how the actual retrieval happens. So how the actual search for the context happens, right? And then post-retrieval, again, you can further improve the relevance of the information that you have retrieved. And so there's, re-ranking, contextual compression, and so on and so forth. And lastly, there's generation itself, right? Like how do you now take all of this context that you've retrieved and get the LLM to answer in the best possible way, right? So there's a bunch of things there as well. Cool. So within pre-retrieval optimization, there's a very interesting technique, which is not very widely used, at least in my anecdotal experience. I've not seen many people leverage this technique, right? So let's talk about the problem that we're trying to solve here, right? Typically, when you have unstructured data, right, that you're trying to make it work within a RAG system, that's not optimized for a RAG system, right? Meaning the information density within your data is typically going to be low, meaning there's like paragraphs and paragraphs of information, and the actual facts are just too sparse within those paragraphs, right? The problem with low information density is that if you build a RAG with just as is, like with your data as is, you end up with too many chunks in the context window, right? When you actually send it to the LLM. And consequently, more chunks results in higher probability of inaccuracy or hallucination. And also the added cost of tokens, added token usage, and your cost goes up, right? So this is like a very basic technique where before even you start building the RAG, you kind of optimize your data that you're going to make use of in the RAG, right? So how do you do that? Um, there are multiple techniques again, right? But one specific technique that's interesting is to use this data, pre-process it with the help of an LLM itself, right? So this is an interesting example that I found where it's a real case study, that of a financial services bank. And they had hundreds of web pages which they were trying to use within a RAG to create a customer service chatbot, right? Now, hundreds of web pages, that's obviously a lot of HTML, raw content. One basic thing to do there is to programmatically remove the HTML, CSS, JavaScript tags, right? So that's the middle box that you see here. But then the information density was still too low, right? So what was done here was that data was taken, sent it to an LLM with a specific prompt saying, hey, you are helping us build a knowledge base, use this input data that I'm going to send you to, summarize that in factual format. And so we use GPT-4 to kind of summarize that data. And then you get a much more information dense context or data, right? And so in this case, if you look at it, the raw HTML had 55,000 tokens, right? The stripped HTML had 1,500 tokens. And the information dense final data that was used in the RAG had only 330 tokens, right? Which is, yeah, which is 4x. Yes, right. Yeah, so you can just use your data and send it along with the prompt. So you basically use that data, send it to send it to GPT-4 along with a prompt saying that here's what you want to do with that data. I can share the prompt maybe subsequently at the end. So what we'll do is we'll take maybe 2 questions at the end of it, so the interest of time, we keep moving forward. But in this case, so that led to a 4x reduction in the number of tokens, right? Which is like astounding, and the accuracy of the RAG, more importantly, went up, right? So that's one thing. Second technique that we'll talk about in the pre-retrieval bucket is query transformation. Some of you might be aware of this, right? Basically, what you want to do is you want to take the user query and apply some kind of transformation on this. Why do you do this? Because oftentimes we humans are really bad at asking questions in the right way, right? So we may have poorly worded questions, we may have super complex questions. And so what you want to do is you want to process that query first, right? So there are a couple of things that you can do. Number one is you can just rewrite that query, right? So let's say you have a poorly worded query that has, maybe typos, maybe grammatical mistakes, and so on and so forth. You don't want to send that to the retrieval to, fetch context based on just that raw query. What you want to do is you want to rewrite that query, right? Again, using the help of LLMs, right? So you use another LLM call to rewrite that query, have it in a much more effective way, send that to the LLM, send that to the retrieval, and then you have a much better chance of getting the right context fetched, right? Another thing that you can do is when the user query is too complex, which requires like multiple subqueries to, in effect, answer that question, you want to break that down into subqueries, right? So again, you use an LLM, you break that question down into several parts, maybe 2 or 3 parts. Then you individually kind of perform retrieval on each of those, and then finally combine the answer together, right? So that's the second technique. Again, another, probably not like case study, but another example that I want to highlight here, super interesting example, is imagine there's this chatbot, right, where customers said, hey, what are the interest rates for your deposits? And the chatbot answers like our interest rates are XYZ. Then the customer asks a completely different topic, right? Like, hey, which credit card is good for travel? And then you answer that. And the customer says, tell me more about the interest rate for that. Right? Now, if you use that query, obviously, you're not going to get the right context from your data store, from your vector store, right? So what do? Option one is you can send this entire conversation history for retrieval. But then can anyone tell me what will happen if you do that? You're going to end up fetching context for the CDs as well, for the deposits as well. And then that's going to, again, introduce inaccuracies or just going to muddy the water when it comes to answering the question, right? So what you do is you take this conversation history, you feed it to an LLM, right? And you ask it to come up with the right query. And then basically, here's an example prompt, right? Like you are examining a conversation. What we want to do is, construct a search query that will be used to retrieve the relevant documentation, right? And so it takes this and it comes with a query saying, what is the interest rate for XYZ credit card, right? And then you use that for retrieval, right? Cool. Moving on, let's talk about retrieval optimization. So let's assume that you've done everything that you can with respect to pre-retrieval. You've optimized your chunking, you've taken care of your query, transformations, you've figured out the right embedding model, and et cetera, et cetera, et cetera. What do you do when it comes to retrieval, right? So typically, when it comes to retrieval, you're trying to solve for, again, low recall or low precision, right? One of those, right? And a lot of times when you're working with domain-specific data, so for example, let's say you're building like a financial services chatbot, right? Which is going to be heavy in terms of financial terms, or let's say you're creating a medical, chatbot or something, right? Again, like super heavy domain-specific terminology, right? What happens when you have domain-specific data is that your embedding model is not going to be able to represent those domain-heavy terms in your data. And so it's going to be poor in terms of performing semantic search, right? It's not going to figure out what is the exact meaning of this domain-specific terminology, and so it's going to suffer, right? So what do you do in those cases? You can either train or fine-tune your embedding models on that domain-heavy data, but a more low-hanging fruit is to use something called an ensemble retriever or a fusion retriever, where you combine old school lexical search or keyword search along with semantic search or vector search, right? How do you do that? You basically, when the user query comes in, you basically send it to two different retrievers at the same time. So kind of parallelly, fetch context from two different stores, right? One is doing a keyword search, one is doing a vector search, right? And then you combine the search results, right? So you take top K from the former, you take top K from the latter, and then you do something called reciprocal rank fusion. How many of you have heard of reciprocal rank fusion? Wow, very few. Cool. So reciprocal rank fusion is nothing new. It's been around for quite a while now. It's a technique which was used widely in the search space. It's basically a technique to combine multiple search results, right, from multiple sources. The way it works is basically you apply this function for the search results from each source, right? So you basically are doing reciprocal rank. So if the context that was retrieved, if the chunk that was retrieved from vector store 1 was at rank 1, then the reciprocal rank of that will be 1 by 1, which is 1. Let's say it was at rank 2, right? It was at the second position, then your reciprocal rank will be 1 by 2, which is 0.5. So you basically just do reciprocal of the rank, right? And you do that for all the sources, and then you combine that to get the average, right? So that becomes your overall ranking, your consolidated ranking, right? And then you take top and from that send it to the LLM, you have a much better result, right? So again, in not exactly a case study, but this is an interesting experiment that was done by Microsoft folks. So what they did is they compared keyword search, they compared vector search, and then they compared it with hybrid search, which means combination of vector and keyword search. And then I think they also compared hybrid plus a ranker on top of it, semantic ranker on top of it, right? So can we do questions at the end? So in this case, if you see, clearly like the percentage of queries where you had at least some high quality chunks within the top 5 results had a huge boost when you did hybrid retrieval. And especially if you combine re-ranker on that, that just takes your game to the next level, right? So speaking of re-ranking, let's talk about what re-ranking is. So we're going to talk about a specific technique called cross-encoder re-ranker. Anyone who's familiar with cross-encoder re-ranker? Yeah, just a couple of folks here. Cool. So typically, the way a vector search happens is that you use something called a bi-encoder, right? A bi-encoder is basically where you pre-process the document, with the help of an embedding model, and you kind of vectorize that. You're basically taking that entire document chunk. So let's say I have this one particular paragraph. I want to store it in the vector DB. You take that, pass it through this embedding model, which is essentially a transformer, and then you kind of have this one single vector, right? One summarized vector, which you store in the vector DB, right? And same thing you do for other documents. When a query comes in, you do the same thing on the query and then do semantic search. You basically use cosine similarity to see how close are these two vectors in this high dimensional space. All right, so that's how a bi-encoder works. The problem with a bi-encoder is that since you're taking this entire document, compressing that into one single vector, you're losing a lot of context, right? So there's some bit of approximation that's obviously happening here, right? And so the search results are going to be of mediocre quality if you use just bi-encoder based cosine similarity based search, right? So that's another technique called cross encoder, right? Wherein you pass both the documents at the same time to the transformer, right? So a model has complete data on both of them at the same time. And then what it does is it figures out what is the similarity between those two documents, right? So that results in much less information loss. And that gives you a much better accurate similarity search, right? How similar are these two things, right? So that's what a cross encoder essentially means, right? So when it comes to re-ranking, what we essentially do is take our data, perform similarity search using a vector search, or you may even use like keyword search, or maybe a combination of those, like we just saw in the previous slide. And then you get your initial search results, right? And let's say that's like 100 chunks of data, right? Now, within those 100 chunks of data, the most relevant piece of context might be at rank 90, right? So how do you get that to the top 5? That's where re-ranker comes in. So what you do is you take these 100 search results, you pass it through this cross encoder re-ranker that we just talked about. And consequently, now your 90th chunk, which is supposed to be a lot more relevant, is going to show up at the top 5, right? Because the cross encoder re-ranker has a lot more context, a lot more data to perform that similarity search, right? So that's what a re-ranker essentially is. Now you might be wondering, why can't we just use cross encoder to begin with, right? Why do we have to do it in the second stage? And the reason for that is a cross encoder is an expensive operation. It's super slow. It's not scalable, right? So you can't do it on like millions of documents, right? So typically that's where you do it, you use it as a re-ranker, as a second stage re-ranker phase, right? So you use some kind of search to begin with, and then you do re-ranking to get the top 5, right? Cool. So we've looked at a subset of techniques for advanced RAG optimization. Like I said, there's just so much more to cover. So hopefully we'll do maybe one more of these sessions subsequently. But the point that I want to make is that overall building a production grade, performant, reliable RAG is very tough, right? It takes several weeks or several months of manual error, trial and error effort, right? Because there's just so many moving parts, so many different techniques and strategies. How do you know what is the most optimal configuration for your RAG, right? For your data set, for your use case, right? For example, if we take a toy example where you had to choose from 5 different chunking strategies, 5 different chunk methods, 5 different embedding models, and so on and so forth, does anyone here know how many different RAG configurations this would produce? 5 raised to 7, right? Exactly. So that's 78,000 different RAG configurations. So obviously, it's not practical for anyone to try out 78,000 different RAG configurations to figure out what is the optimal one for my data and my use case, right? So that's the problem that we are solving at RAG Builder. And this is where what our technique is, basically our approach is to do hyperparameter tuning on the different RAG parameters, right? So if you take, like, for example, chunk size, how do you figure out what is the right chunk size for your data, for your use case, right? We will tell you based on hyperparameter tuning. So for those of you who are not familiar with hyperparameter tuning, it's a ML technique which you use to figure out what are the optimal values from a large set of options, right? So it's a well-known technique in the ML field. We are applying hyperparameter tuning to RAG, to the parameters of a RAG, right? We also come with a bunch of predefined RAG templates. So for example, as you saw, there's, ensemble retriever, hybrid retriever, there's, query expansion, query transformation, right? You don't have to reinvent the wheel if you're starting to build a RAG. We come with a bunch of predefined RAG templates, right? And then we do a bunch of other things like synthetic test data generation to automatically evaluate your RAG and so on and so forth. But without much further ado, let me jump to the demo to quickly show you how does it work, right? And by the way, installation is super straightforward. If you go to ragbuilder.io, there's a handy command. You can just copy that, install that. All it does is it uses brew to install a couple of libraries and does pip install ragbuilder, right? So I've already installed ragbuilder. So I'm going to go to my terminal. I'm going to just start this from scratch. Right. So I just go to my terminal and type in RAG Builder, and it's going to spin up a UVCont server based on Fast API and bring up the browser shortly. So all of it runs locally, by the way, within your own system, within your own network. So data is never leaving your system or your network unless you're using a third-party AI service like OpenAI or something, right? So this is the dashboard that you get when it starts running. And like I said, it's running locally. So let's say I'm creating a new RAG. I just click on new project. I given a description. So let's say we're creating a documentation chatbot on LangChain. Let's say I am Harrison Chase. I want to create a documentation chatbot on LangChain, right? All of you are familiar with LangChain, by the way, right? Yeah, awesome. So I just give it the source data. So I've already scraped LangChain documentation as markdown files. So I'll just give that data, right? And like I said, we come with a bunch of predefined templates. So that's the first option that you see here. And then there's custom RAG configurations. This is where the hyperparameter tuning happens. So this is where we build your RAG ground up on the fly, right? So let's go ahead and click next. So these are the templates that we have. We just launched this a few days back, so it's not exhaustive by any means, but there's a handful of interesting ones like query rewrite, like we just discussed, query expansion, step back prompting, semantic chunker, hide, hybrid radic, etc. Right? You can select your embedding model and the LLM. Let's go ahead and click next. Now in this particular screen, you can further customize your RAG, right? This is for your custom RAG configurations. So you can select what kind of vector database you want to use. You can select or unselect maybe a specific chunking strategy if you're not interested to use that, and so on and so forth. But basically, you get to select or fine tune or have granular control over all the moving parts of a RAG, right? Starting from your chunking to embedding model, vector database, retriever, re-ranker, compression, and so on and so forth, right? So let's go ahead and select these compression techniques as well, and then your final LLM as well. Right? And then advanced settings, as you can see, we do Bayesian optimization hyperparameter tuning by default, right? So it will run for 50 times and try to figure out what is that optimal RAG configuration for your data and use case. Now you might think like, how do we do hyperparameter tuning? What is it trying to optimize for? And the answer is we try to optimize for your RAG reliability or your RAG accuracy, right? So we use an evaluation framework, which again, you have control over. You can pick whatever RAG evaluation framework you want to use. We use Ragas by default, if you have heard of it. It's an open source library for evaluating RAG systems. There are a couple of others that we are still building. It's still work in progress, but there's TrueLens, there's Aries, and so on and so forth. But basically, you can pick that. More importantly, you can specify what data do you want to use to evaluate the RAG, right? When I say what data to use to evaluate the RAG, you need to provide a question and ground truth pair so that we can check each RAG configuration to see how close is this RAG answering to the ground truth that you have provided, right? So it's just a two-column CSV file, right? Like a question and a ground truth. You can either bring your manually curated data, right? Or we can generate it synthetically for you automatically based on your source data, right? So in my case, I already have synthetic test data. So I'm just going to go ahead and point it to that. Go ahead and click next. We review all the selections here and we hit confirm, and it's going to start spinning up. So if you notice here, I don't know if it's visible out there in the back, but there are 312,000 different RAG configurations based on the selections that we just made. So clearly it's like impractical to test each one of those. That's where the hyperparameter tuning is going to run for 50 times and try to figure out what is that optimal needle in the haystack, optimal configuration within that 300,000 different RAG configurations, right? In addition, it's going to use all those templates that we provided, right? So that's the gist of it. As closure, I'm going to show you how does it look like once it has completed. It may take a few hours to run depending on the volume of the data and the number of questions that you're using to evaluate. So I'm going to show you a run that was completed successfully. This is what it will look like once it has completed. Let me zoom in a little bit. So these are all different RAG configurations. And you have, as a developer, you have all these metrics showing what was the accuracy, what was the answer correctness like, what was the precision like, what was the recall like, what was the cost per query, what was the latency like, and so on and so forth. So if you see the first one, right, like this was the best, most accurate performing RAG, right? 0.91, 91% accuracy. But in terms of latency, it wasn't as great, right? Like it took 7.86 seconds on average for each query. I, as a developer, might think, hey, you know what? I need a lower latency RAG. And so if I just scroll a little down here, I see there's another one with 3.44 seconds. Looks much more interesting to me, kind of in the same ballpark of accuracy. And if I expand this, I see that it used chunk size 1,000 with an overlap of 200. It used a bunch of different retrievers, vector similarity search, BM25 retriever, which is for keyword search, and then it did a parent doc, full doc retriever, and so on and so forth, right? I can even go to view details and look at individual question and answer level. What was the accuracy like? More importantly, I can click on view code snippet, and with a click of a button, I have performant production grade RAG for my data and my use case, right? So that's the whole value prop that we're trying to bring. We are completely open source, completely free of cost. So please do check us out. Would love to get some feedback from all you awesome folks who are trying to build RAG applications. Just to kind of close this out, I have this 1-minute survey. It would mean a lot to me if you can just answer a couple of very quick questions. Plus, we are offering free office hours. So if you're struggling with your RAG application, there's a link at the bottom of this survey, which you can sign up for. And I'll provide my expertise. My co-founder is also an expert. He'll come in and help you out with your RAG bottlenecks or your RAG issues, right? So thank you so much for taking the time to listen to me. This was amazing. I hope I was able to add some value to you folks, but really appreciate it. And a huge shout out to Deep Tech Stars, Neo4j, and Nasdaq. A hat tip to Nihal and Sid for organizing this amazing event. Thank you so much, folks.
If you're serious about a career in AI, follow Deep Tech Stars on your favorite social media platforms.